manufacture of stainless steel in sizable quantities has been carried out using electric melting since about 1930. However, it wasn't until the late 1960s that the single most significant development in production techniques took place, with the advent of the argon-oxygen decarburization process. AOD processing soon revolutionized stainless steel manufacturing worldwide, with its technological and economic advantages dramatically reducing the overall cost of the finished product. British Steel was quick to recognize the potential of this revolutionary secondary steelmaking process and installed 2 units in the early 1970s, a 15-ton plant at Stocksbridge and a 40-ton plant at Panteg in South Wales. Then, looking to the future, they commissioned an AOD unit with 130 tons capacity here at Shepcote Lane in Sheffield in 1977. At the time, this was the largest such unit in Europe, designed to produce over 350,000 tons per year of high-quality stainless steel. It's fitting that this massive investment in stainless steel production should take place in Sheffield, the birthplace of stainless steel, where Harry Brearley was born and worked. In 1913, he discovered that a 13% chromium steel didn't rust when exposed to corrosive environments, and was first to coin the name stainless steel. Since those early days, Sheffield steelmakers have developed both the process and the qualities of stainless steel to meet the demands of customers throughout the world. The plant, codenamed SMAC, Stainless Melting and Continuous Casting, has justified the company's massive investment by earning an enviable reputation for productivity, quality, and safety. All stainless steel production starts from a mixture of high-grade scrap, nickel and ferrochrome. Up to 25,000 tons of stainless and mild steel scrap may be stored at any one time in an area to the northwest of the plant. On arrival, the scrap is inspected to ensure that it complies with the quality requirement, and if necessary, a sample is taken and sent to the laboratory for analysis. It is then stored in either the gantry pens, concrete bunkers, bulk storage areas, or in any one of up to 340 scrap storage skips.
Well, when we receive scrap into SMAC, the main thing we're looking for is dirt. We're also looking for material which is not up to the specification, which is supposed to be. The main scrap we get in is 18.8, which is 18% chrome, 8% nickel. That is the basic scrap for SMAC. We use more of that than anything else. What we're looking for is any material which does not conform to the specifications.
A computer-based system known as least-through cost mix was installed at the outset for calculating the most economical mixture of raw materials to be used for each cast. The computer indicates a best overall steelmaking strategy based on the current market price of each raw material and the processing costs, and is fundamental to the economics of the operation. All raw materials, whether scrap or ferroalloys, are weighed and assembled in skips in the service bay, as they are called up by the least-through cost mix system. The important ferroalloys, such as ferrochrome, ferronickel and ferrosilicon, are stored in pens inside the melting shop. The most valuable ones are kept locked in a high-security compound. Power shovels are used to scoop up tons of ferroalloys at a time and load them into skips. service bay crane loads the skips into a bottom opening basket, standing on a rail-mounted transfer car. The material is then transported by the car into the ladle bay area, ready for loading into the electric arc furnace. At this point, the steel-making process becomes the responsibility of the melter, who operates the furnace. The furnace produces 125 tons of molten steel in each melt. It uses 3 600mm graphite electrodes to create an arc, using enough electricity to power a small town in the process.
This is where we melt the steel. We use 3 electrodes to create an arc to melt the cold scrap to a semi-fluid state. We inject oxygen to bring the temperature up to 1620 and the silicon down to a desired level for tapping to the AOD.
When the charge has been melted to the required temperature, which normally takes 1.5 hours, it is tapped into the ladle for transfer to the AOD vessel, and a sample is taken for analysis. Because of the inherent dangers present whenever liquid steel is handled, no one is allowed to work in the melting shop without full safety equipment: fireproof trousers and jacket, safety helmet and molten metal visor, and of course foundrymen's boots. Having absorbed the melt impurities, the molten furnace slag is poured off to ensure that only metal is transferred to the AOD vessel, and then the charge is weighed. Slag is removed from the bay by a specialist slag transporter. The metal content is recovered for reuse while the residual slag is turned into roadster. The melting shop is linked to the analytical laboratory by a high-speed pneumatic sample carrying system. Computer-controlled instruments in the laboratory provide rapid analysis of steel-making samples and raw materials. Analytical results from the laboratory computer are displayed on the melting shop computer, which is also central to the production planning and control system in operation. The metal weight and the analysis of the sample form a starting point for complex calculations that the steelmaker must carry out in order to control the AOD refining process and ensure that the final product falls within the tight specification tolerances. Once the molten metal is charged into the refractory lined vessel, the mixing and stirring begins, using critical combinations of oxygen, argon or nitrogen to increase the temperature, stir the molten metal, and at the same time reduce the carbon content.
This is the AOD control room. The molten metal from the arc furnace is transferred into the AOD vessel, where we refine it to meet the customer's requirements. We inject oxygen and nitrogen or argon into the molten bath to reduce the carbon content. The oxygen also increases the bath temperature, which we control by making various coolant additions. Once we get down to the required carbon level, we add a reduction mix to reduce the oxides in the slag back into their metallic forms. Afterwards, we add a desulfurizing mix to further reduce the sulfur level and then make small trim additions to meet the final specification.
There are in fact 3 of these AOD vessels which ensure that all refractory relining can be carried out away from the steelmaking area without affecting production. The condition of the refractory lining is inspected each time the heat has been tapped. When a new vessel is brought into use, it must be ready and on preheat before the substitution in order to ensure a smooth continuity of operation. Once the AOD vessel has been tapped, the cast then passes to the flushing station. Here it is stirred with pure argon. using either an injection lance or porous plug in the ladle bottom to achieve the correct uniform casting temperature, which as a process requirement must be controlled within a 10-degree band. When the temperature of the steel is correct, the ladle of steel is taken to the continuous caster. The rotating turret takes the ladle from the steel-making bay to a position over the casting machine, from where the molten steel is teamed into the ton dish through an enclosed refractory tube which mates precisely with the gate valve in the ladle bottom. It is the ton dish which provides a constant flow of steel to the concast mold, using an electronically controlled flow management system. Observation of the liquid steel and feeding of the casting powder still has to be done by operators standing very close to the mold. Again, as with the arc furnace, the wearing of full safety clothing is essential.
The liquid steel comes here straight from the AOD vessel. We pump argon through it at the flushing station to bring the steel down to the right casting temperature. The steel is then poured into the casting machine through a ton dish. From the ton dish it flows into the mould through a submerged entry nozzle, where it is progressively drawn down the machine and slowly cooled. When the steel emerges from the machine, it is cut to required lengths.
Several ladles may be teamed consecutively in the same cast, a process known as sequencing. The casting supervisor has the critical task of ensuring that these standing ladles will all be within the set temperature limits when they are subsequently teamed into the ton dish. When the slab of stainless steel emerges from the spray chamber and into the straightener, solidification is complete. As the new slab leaves the straightener, the dummy bar disconnects automatically, and the slab is then cut to length by a flame cut-off machine to a predetermined cutting plan. The run-out of the continuous casting machine takes slabs into the slab processing bay, where they're tagged for identification purposes and are cooled either above ground or in a temperature-controlled pit, depending on the type of material produced. In the slab processing bay, the cooled slabs are inspected prior to grinding. The extent of the grinding required may vary from full surface preparation to intermittent spot grinding, depending on the condition of the slab surface.
Grinding the defects out, this is a tramline grind, one of the many types of grinding that we do down here. It's ground down the edges and we have to provide a surface finish that falls within the standards.
When grinding is complete, each slab is tilted under high-intensity light for a final rigorous inspection and surface roughness check. The next destination is the hot mill, where the slab is rolled to either coil or plate. Several hot mills are used to ensure that both the required throughput and quality are achieved in readiness for the finishing operations. The quality of our stainless is guaranteed by a comprehensive quality management system which embraces every product and process from material receipt right through to dispatch. Precise performance in all activities is needed to ensure that our customers' requirements are always met. Visual display terminals are located at every major operation point throughout the plant, ensuring all involved are kept well informed and are able to carry out their duties effectively. The processes used at BSC's stainless melting shop are the result of many years of development. This development continues to find new steels and better production techniques, keeping Sheffield in the forefront of world stainless steel production. Before going round the melting shop, you're asked to listen carefully to the following do's and don'ts, which are intended to ensure that you have a safe visit. Do wear the appropriate equipment provided for your safety. Do stay close to your guide and follow his instructions, using the gangways and walkways provided. Do look where you're going and watch out for cranes, vehicles, manholes, excavations and other obstructions. Do keep clear of molten metal and sparks. And do keep clear of machinery in motion and control desks. Do not touch or pick up any object. It may appear cold, but could be extremely hot. Do not walk between railway lines or pass between wagons. Do not pass under loads suspended from cranes. And do not lean over handrails. Thank you for your attention, and we hope you enjoy your visit.